to talk about a bit more about 3D vision. And so, like I said before, when I was answering the question, a lot of things in 3D vision is not, it's still conventional. It's using pre-deep, pre-deep learning uh, approaches. Uh, but now we are seeing like many methods which are combining the things we learned on the first day with in a deep network to create what you call a depth learning, a depth sensor from just a single camera. So this is color coded. Okay, let's turn off. So this is the color indicates the depth. So you see the roads are you can see they're somewhat planar, and it also computes what you call flow. So flow is the difference between a pixel, an object pixel in one image to the same object pixel in another image. So corresponding between the corresponding points. So you can see it can detect cars and such things. So this was presented in this year using what we learned using equations what we learned on the first day. So in case you're wondering if this will be useful for AI and AI applications, definitely it will be useful. For example, this particular setting could be very useful for autonomous driving, because then you can see the depth of how far the people are, how far the cars are, and where are the surroundings, how far they are, and such things. So let's go back to where we left off last time. Before that, I think there was some confusion about the lab session, and a lot of people were wondering why, when we project the points, after we project the points, why we are dividing, right? So the thing is, we have to go back to. I don't know if you're still wondering, or maybe you found a solution. No? So let's go back to our very early slides. So here you see the point is represented, the 3D point is represented as homogeneous 3D coordinate with one extra point, one in the end. And the image coordinate is q, uv1. So if you want to express in homogeneous coordinate, you can express as lambda times uv1. So all of these points are the same. But if you visualize it in just 2D, then you have to get uv1 before you extract uv. Do you get what I mean? So you have to extract, before you extract the image points to visualize, to see where the projections are, your image coordinate might be lambda times, let's put lambda here, uv lambda. But before you extract this, you have to get something, something 1. Then only this coordinate is in Euclidean space. Otherwise, this coordinate is not in Euclidean space. Right? So that's why to visualize, we have to take, you have to divide by the last component after projection. Now, let's continue to triangulation. So we completed the essential metrics last time, and we said that we can decompose the essential metrics into rotation and translation orientations of the camera. So you have now corresponding points. So 2 corresponding points, and you know the essential metrics, and now you can extract the pose of the cameras from the essential metrics. So you basically have to decompose the essential metrics into T, X, and R. If you have the corresponding points, so you will have a unique solution for T and R here. Then you have the camera matrices, right? M1, M2. Then what you can do is you can draw lines, so rays from 0 origin to Q1 and so on, and see Q2 there to get P. So now this is again a linear algebra, right? How would you draw lines and connect if you are doing it in a computer? Do you draw in the screen, or how do you do it? Intersection of a line. This is something you have been doing since me too. I've been doing since grade 7th or 8th, right? Like you draw some lines and you find solution, right? So how do you do it? Solving equations, right? So what are the equations? So this is what you need to solve in today's lab session. Can anyone volunteer? No one? You volunteer. So, I mean, it's quite straightforward. There's nothing. So we say M1 times P is Q1. Is there any problem? M1 projecting P gives you Q1, right? So M1 is 3 by 4 matrix, and P is 4 by 1, and Q is 3 by 1. So remember that we are expressing P in homogeneous coordinates. So it could, so all 4 of them are variables, right? So this is clearly, you cannot solve it. That's why, because M is 3 and N is 4, so this is underdetermined. So you are in this state where M is less than N in this, different cases of solving equations. So you cannot solve it, and that's why we need second camera, where we have M2P equal to Q2. So now you just stack them, right? It's the same P. This P and this P are the same. Do you agree? And you have 2 cameras, and now you can stack them and just solve for P. So this is called triangulation. So mathematically, triangulating means you're solving these 2 equations together. So now let's go to the part where we talked about correspondences, but how do you extract them? And how do they look like? So here, this is an example of 2 pictures of 2 different views, of a temple, I think, and you're trying to match, all the corresponding points between these two images. So here you see some of these points. Here, a lot of points, they are matched correctly. So the door, like side, I guess goes to here. But some of these points you see, like this one, is getting matched to nowhere here, right? And this point, is similarly going to very wrong correspondence. So do you agree that this is wrong? So these points are wrong, but most of the points are correctly matched between these two images. So we can, as we saw in the morning's class, we can use ransack to remove these wrong measurements using the epipolar equations. So this is what you will do in the lab session as well. So just make sure that, yeah.
How can you get the points wrong?
Because so this is the next slide. So to match these two images, so the pixel locations are at different positions, right? Because the views have changed. So you need to use some way to characterize the points and describe them with some representation that Vishesh was talking about, and then compute distances between these representations, and then get the matches. So to do that, we use still a pre-deep method of 2004. It's called Sift. So this is scale invariant feature transform, which means that it can detect, it can match. So before matching, we have to describe. It can represent features of points similar despite changes in illumination, changes in views. So the same point will have the same features, even if they are taken from different angles. So that's how you then create a vector, and then that you can match. So we'll go into that now. So how do you do Sift? So Sift is a handcrafted a feature extraction. So what you do is you go through a series of steps on the image. So first you take an image. Let's say you took this image, and then you apply Gaussian filters. So basically you're blurring in different scales. So a number of scales, right? Many scales. And then at each point, what you do is you have different scales of these Gaussians stacked one after another. So you take a patch in the image. Let's say this. So this is one of the Gaussians now, and these are the neighboring Gaussian scales. So like in this case, for example, this is the center, and this is the top one, and this is the bottom one, right here. And then you compute the differences between these, between the points, between the center point and all other points. So similarly, you do it for all these levels, and then you extract the maximum or minimum, either maximum or minimum, because you have a series of vectors of these differences, and you extract the maximum or minimum. And then what you do is, where there is maximum or minimum, you have you identify that those points are descriptive, and those scale where you have the maximum is also the descriptive scale. There, then you go through extraction of features. So first you identify the points which are descriptive by doing this difference of Gaussians, and then you go through extraction of the features on those points. So to extract features, you take patch again around the point, then you compute image gradients. So here you have a 4x4 patch, so patch, and they are even segmented into more grids. And there you compute the gradients. On every patch, you compute the gradients of the image. So this is a bit involved, but you don't need to remember everything, but just the gist that how you what kind of operations do you use. So Sift descriptor is basically made from gradients. So you have many gradients, and then you compute the histogram of these gradients. So you say like, you compute the gradient histogram of the orientations of the gradient. So some gradients will be in this direction, some will be in this direction. So you just cluster them and take collect gradients facing this direction in one, and gradients facing this direction in the other, and you sum them up. So that becomes something like this. And then you just concatenate all these magnitudes in 8 different directions. So what you get in the end is the direction of the gradient of the histogram. The histogram of the directions and the descriptor from the Sift feature extraction. At the end of this stage, you identify some points which are descriptive, and you have a vector of 128 real number. So use this to extract features like this, points like this, and features on them. So to match, you just take the closest feature. Let's say you found this point, and then what you do is you extract the Sift feature here. Then again you extract Sift features, all these Sift points here, extract all the features, and check which of the feature here is closest to the features here. So all these points have 128 long feature vectors. So you can also use this kind of Sift. So Sift is just one method. There are many other methods, and for now it's only used for mostly for extracting and matching correspondences. So if you want to do more like segmentation, or let's say describing images, or object identification, then you don't use Sift anymore. So that's a good thing, because this is quite complex. The method itself is like a series of multiple steps that you have to really go through, one by one, and very handcrafted. And whereas deep learning, you can just, you can train your own extraction method by yourself.
I think it links to what we said in the earlier lecture about, I showed the images of kittens, right? And there the idea was finding the distance between the images itself. So the whole image was one object, and you wanted to find the closest image, closest point. While here the problem is slightly different, I guess. Well, many of you know that, is you have an image and you have another image and you want to find for those pixel locations, where are the most interesting points consistent across the images, and what's the distance between these, or find a metric so that you can find out which one is the closest point. So for us, it's quite obvious if when we see here the temple or corners of the temple or certain parts of the windows, we know where it is in the another image. But now here the whole idea is, because that's the correspondence. So if we have two images of the same person taken from a slightly different directions, then we know immediately this is nose here and this is nose here. But the algorithms, they don't know where what lies. But we still want to figure out a way to find the correspondence. So the trick here is to be able to first find these interesting features which are consistent across scales, in this case, and then also represent it. So you see the representation earlier, we were talking about representing the whole image. Here the whole method is trying to represent. What is it trying to represent with Sift? Correspondence is what we build after that, but the representation itself with the feature vector, what is it representing? So it's representing point in some sense, but what would have happened if we just took the distance between because this is an image, so there is pixel values, right? So intensity value at each location. What if we just take a distance between that intensity value against the another one, and let's say we want to find the corresponding point of this point image. What if we take the distance, compare the distance of this pixel value against all of those? Would it make sense? No. Why? Lighting? Yeah, because just one point or one pixel cannot really represent the sense of what we see as a corner, right? There is a certain neighborhood information that needs to be there. So that's what, when the Sift does this convolution, this Gaussian convolution, it's just one kernel, choosing a particular set of weights and doing the convolution that we did earlier. But it wants to be consistent across scales. So there's this scale invariance, that's why there is hierarchy, the different levels. Then it tries to capture the information that is here in its neighborhood and then represent it with a vector. And it wants to do it in such a way that the correspondence that we see as humans lie close by. The points, the feature vectors lie in this space of this 128 dimensional vector. Right? Yeah, so that's just wanted to give you context from what we said earlier.
Yeah, nice. So we'll not talk much about Sift because we only use it as a way to form correspondences later on. But it could be, Bishes is right, it could be used as a representation for your image or for your image patches or many things. So this was actually used as a descriptor to represent images using what you call bag of words, if you have heard of this term. So what you do is you cluster these Sift features and take the centroids, and those are the collection of these things are the bag of words. So, but bag of words, there are modifications to it. Now, like many deep networks try to replicate similar mechanisms and do actually better than these kind of how do you call adding or concatenating many features and creating the right feature. So we will only introduce slightly multi-view triangulation. So the whole 3D vision we're talking about from in day one, we call it structure from motion. So it is actually structure and motion, because structure means your 3D shapes, And motion means your camera, how much has changed, or where is the camera from multiple images. So what happens is in structure motion is you have multiple views of images, and you get both structure and motion at the same time. This is actually surprising because, in fact, if you see, let's go back to some slide here. The structure actually depends on the motion, right? If the motion is off, if you predicted the rotation or translation incorrectly, then you would never get the point correctly. You would have the wrong pose and the wrong correspondence, and you would match somewhere. You would triangulate somewhere else. Whereas in structure from motion, you are solving this together. As soon as you have E, you have both 3D point and the motion. So what we will do is just see. Remember the first few slides we had where we had reconstructed 3D of Rome or 3D of many like cities like Zurich and those places. So the way they do it is we just describe them in few sentences. So this is first you have to, of course, match correspondences against different images. Then you triangulate with two views. So in each pair you take the images where they match correctly, and then you triangulate points, right? You triangulate points, and at the same time you have the poses of the cameras with respect to each other between two cameras. Now you have to translate these poses to a common reference, which is usually the first camera. Something like this. Sorry. Yeah. So, for example, you have I0, sorry, this is I, comma 0. This is your first camera, and R1, T1 is second camera, R2, T2 is your third camera. When you triangulate points between these two, it will be in the reference, in the coordinate system of this camera, which is the origin. If you triangulate points between these two cameras, it could be in the reference of this camera, right? And let's say you call it P prime. So how can you, but this P prime will be expressed in coordinates in the reference of this second camera and not the world origin or the first camera origin. So what you need to do is you need to transfer points triangulated in other cameras to the common reference. So can you think of how you can do that? So you can just draw the line between here and here. So this will also be the part of your lab exercise for today. So you have P prime expressed in terms of the camera, which is in R1, T1 orientation. So the first thing you have to do is rotate the point back in the first camera orientation. and then you need to translate back the point T1. So what you do is you do P new equals to R transpose P prime minus T1. That after you do that, your points will be in the common reference, even the ones triangulated between these 2 points. So if you triangulate between this camera and use this as the first origin, it will already be in this origin. So you don't need to transfer the points. So the next part is what we call bundle adjustment. So this is supposed to be bundle adjustment. This is an application of the optimization we studied today, especially Levenberg-Marquardt. But we will not, I don't think we will have time to do this in the lab sessions. What happens is that sometimes you have noise in your correspondences. They are not wrong, but they are slightly off. Or because of that or whatever, your pose of the camera, of the 3 cameras, are not exactly correct. So if that happens, and you want to, let's say, you match these 2 camera points, and you triangulate to some point, and this camera is slightly off, and you match the same point here. And if you triangulate, let's say it's off by this margin, if you triangulate, it will if you try to triangulate, it will go somewhere else, because the pose is slightly off. So here you can already think of, like, this is an optimization problem, right? So you know that the correspondences. So in this case, let's say that the correspondences are correct. You know that the correspondences are correct. What is incorrect is that somehow your pose is not accurate, is slightly off. So what you can do is you can change the pose. Okay, something happened. So you change the pose slightly so that when you project the 3D point, it goes to the right correspondence. Which means that you minimize the reprojection error. So can anybody write the reprojection reprojection equation for me? Can you tell? You don't need to write. Like we were doing this here, right? M1P equals to Q1. So what you're doing is you already computed P, but you are reprojecting it to see where it goes. And then you can do, now we have 3 cameras. So you know that you have to satisfy your camera should satisfy these equations. M2P equal to Q2, M3P equal to Q3. Then however, if you take P and see this, that they are not actually accurate. So instead of just recomputing P, normally what is done is that you also change M1, M2, M3 little bit so that these equations are perfectly satisfied. And this is called bundle adjustment. This is just a fancy name for the optimization we studied today. So we can formulate it. So in optimization, we said that we optimize usually in terms of some variable, right? So here, if we optimize in terms of only P, this will be linear least squares. Because their M1 are not variables, they are linear equations. If we start to optimize with both M1 and P, then this becomes nonlinear optimization. And that's when we use something like Leavenworth-Marquardt, or Gauss-Newton, or gradient descent. So your variables in this case would be R, the rotations, and the translations. So you optimize for rotations and translations, and the 3D points, such that these errors are 0 or less. And this is mostly the final step of structure from motion. And you will have, at the end of this stage, you will have a sparse reconstruction of your surface you want to get. So normally, even if you don't do this refinement, you should get something that is, okay to look at. So I hope in the lab session you will be able to get some 3D reconstruction from these 3 images I have uploaded. I didn't talk about, so I need to talk about one more thing before that, before we go to the lab session. In this equation, we said E, we know that E essential matrix is you cannot compute the scale of E, right? No matter which scale you choose, they will still satisfy the equations. So you don't know the scale, meaning that you don't know the scale of the translation. So what you should do is, if you have 3 different So what happens is, if you have 3 different cameras, you compute the rotation and translation with this camera, with this, from this essential matrix, and rotation and translation from this essential matrix. The rotations will be correct because the rotations have no problem, but the translations will be in different scales. So T1 will be in different scale and T2 will be in different scale. So you need to make sure that they are the same scale, and you need to fix it. So this is a bit tricky, right? Because you cannot compute the scale from just by just matching. So what you can do is, you can also match this image to this image, right? You can match the first image to the third image as well. Then you get some R and T. So in the end, what you have is, you have 0, and then you have T1, and you have T2. So you don't know the scales, right? So you put A T1 and B T2. So you also have, so let's write it this way. We write T1, 2 for translations between the first camera and second camera, T2, 3 for the translations between the second camera and third camera, and T3, 1 for the translation between third camera and first camera. So we don't need to write a variable for T3, 1 because now everything will be computed with respect to T3, 1 scale. So can you think of any equation that will be satisfied here? Just draw a line between, here and call them t. Do you have a pen and paper? Can you see? Note that t1, t2, t3 are vectors. So I want you to find a way to compute A and B to get the right scale. I think as soon as you connect these 3 points in a triangle, then you basically solve the problem. This is T23, and that is T31. So you should be able to come up with some vector equation there. Did you figure out? Basically, if you go around the triangle, then the sum should be 0, right? Yeah, it's just simple vector mathematics. So don't forget the A and B's, because you want to compute the A and B's. So what you will get is a bunch of equations in the end, which should be overdetermined. Is it overdetermined? Yes. Unknown is A and B. You already computed T1, T2, T3. Yeah. Yeah, something like that. Yeah, yeah. Depends on the direction. You just need to make sure. Yeah, 1, 2, 2, 3. Yes. Could you go and do there to help your friends, because they are not enough motivated now. Yeah, in the board. Thanks. Maybe you need a mic.
So using vector addition will first define the relationship between those three vectors.
Maybe you
So
want to draw the figure so it's clear, right?
So
Maybe you need to extract the components.
yeah,
right? Yeah.
T12x, T12y, T12z, T23x, T23y, T23z, is equal to T13x, T13y, T13. So Ax equal to B,
Yeah, okay,
and then we'll solve for x.
nice, thanks. So let's in the lab session. So first you are going to match these three images which are in the folder. Then extract the essential matrix. After that, you should get you decompose the essential matrix using some function. We'll not go into detail. You can look it up what it's doing, but we don't need to go into detail. After that, then you will do these operations, and you should get some small, not very dense, but somewhat like 3D structure. Do you have any questions on this? Otherwise, we can start the lab session sooner and complete the. Did you have any problem with the last session? Were you able to do this? The goal of the last session was to compute the essential matrix. Yeah. There is one more thing. There is one more thing. When you compute the essential matrix, we said that this is rank 2. This is a rank 2 matrix, right? So how do you, when you solve it using these linear relations, you get a least square solution, which is an approximate solution. This solution doesn't necessarily is in rank 2. It may not be rank 2. So you should first enforce, after you compute using these equations, using SVD, what you should do is you should enforce that afterwards. So we just talked about SVD and you said how it is related to rank. So we can also use SVD to enforce it if the rank is different in a what we call least square way. So what you do is you simply decompose E, simply do SVD of the essential matrix. So you have E, so U, S, V transpose, right? So S matrix, if it's not, so in general, S here is 3 by 3. So everything will be 3 by 3 matrices because the essential matrix is 3 by 3. So the S matrix will have will be a diagonal matrix ABC. For E to be rank 2, what you should have is E times B equals to US, and E times V3, the last column, should be 0, right? Because the matrix should have one kernel, non-zero, with non-zero vector. Which means, what does this mean? This means that the last element of the diagonal matrix should be 0. So you can just do it with matrix multiplication. If this is 0, no matter what the content of U is, E times V3 will be 0. And then you will enforce that E will. So what you do is now is once you make sure that C is 0, you just write like this. You directly enforce S equals to rank 2, and then you recompute E using the same equation, USB transpose. And then you get new E, which is rank 2. So you should do this before you decompose the essential matrix into rotation and translations. Is this somewhat clear? Or clear? Should be clear. I think the confusion might be coming from the fact that you have never tried to multiply these two matrices, a diagonal matrix and some matrix. So if you multiply some matrix with a diagonal matrix, the columns will be scaled. This will scale the last column. This will scale the second column. And this will scale the first column. So if the last column is scaled to 0, then you have the result of this will be 3 by 3, but with last column 0, which means you have E times B3 equal to 0. Right? All right. So time to work. Thanks, everyone.